All right, so Newton's law of cooling, it's called the Newton's law of cooling, but it also applies to heating. So if an object is increasing in temperature, it would still follow this model. All right, so don't get thrown off if that happens. The rate of change, all right? So again, the term rate of change could mean a slope. It could also mean derivative, right? It depends on whether or not it's talking about over an interval or if it's talking about at an instantaneous level, so at a particular moment. If it's instantaneous, then it's a derivative. General rule of thumb is it's instantaneous unless they tell you otherwise, right? So if they tell you that the rate of change from time t equals 2 to t equals 7, that's over an interval. But if they just say rate of change, they're talking about a derivative. The rate of change in temperature of an object, so dt dt, d capital T for temperature, d lowercase t for time, is proportional, all right? So proportionality is just talking about a relationship between two variables, a direct relationship, and the only difference would be some factor k, some unknown numerical value that is a multiplier of one variable, all right? So proportional to the difference between the temperature of the object, which again we're calling T, and the temperature of the surrounding medium, which is we're calling T sub m. All right. Well, it comes from two places. One, I mean, if you're a memorizing kind of person, it comes from the model, f of x equals kx. But a proportional relationship is just talking about two variables being related to one another. So if I say, I'll use, instead of x and y, I'll say a and b. A and b are related to each other in some way. All right, the relationship is direct equality, in which case a equals b, or maybe a is twice the value of b. As a increases, b will increase, but b is going to increase at a faster rate. Right? Maybe it's half the value of b. Right? The possibilities are endless, and so to account for that, we say just simply that a and b are related by some factor k. And it doesn't matter that it's k, it could be anything, we just tend to use k. Right? If it's inversely proportional, that's saying that one variable is increasing while the other is decreasing. So a would be equal to 1 over b, in which case you'd still have that multiplier k slapped on, but you'd have one variable in the denominator. That was an excellent explanation. Well done. I'm going to scooch this over. Group, boom, and slide to the left. Okay, so let's get some numbers in here. A 12-ounce glass bottle of liquid is placed in a freezer and kept at a constant temperature of 20 degrees Fahrenheit. So dt dt is equal to k times t minus 20. The initial temperature is 70 degrees, so that's at time t equals 0. After 5 minutes, the temperature is 50 degrees. How much longer will it get down? Will it take to get down to 37 degrees? All right, so at this point, we want to work in general terms because everything that they're talking about after they mention the constant temperature is relating temperature and time, not change in temperature. So I don't have a relationship between strictly temperature and time here because I have that dt in there. So that dt's got to go. All right, so I'm going to clean things up, and cleaning things up means get all like variables on the same side. All right, so 1 over t minus 20 dt. You put the k wherever you want because it's constant. Is equal to k dt. Uh, but it happens. Mistakes happen all the time. Me actually catching it is what I'm shocked by right now. So the capital T's go to the left, everything else goes to the right. If you want, you put the K with the left-hand side, but I think it tends to make things a little messier. All right, so we're going to anti-differentiate. All right, so take the antiderivative. This is an old rule that you may or may not have a whole heck of a lot of experience with, and I'm kind of jumping the gun because we'll formally address this topic down the line, but it kind of fit here, this particular problem, so we'll do it now. Oh, and fun fact of the day, Alexa knows calculus. I asked her some questions today, and she got them all right. So ask Alexa if you get into a jam. That's wonderful news. I don't know if Siri knows calculus. You could try that, but she doesn't. No, Alexa knows. I mean, you got to say it correctly so that she understands it. But if she knows what you're talking about, she'll answer your question. Okay, maybe I'll bring one in during a test. I'm not joking. All right. So a rule that you may or may not remember. The derivative with respect to x of the natural log of u. Does anybody know that one? 1 over u times the derivative of the u, right? All right, so this is the rule for now. Later on in the course, I'll show you where that rule came from, and you'll never have to worry about remembering it because you'll understand its origin story, and that's the name of the game for a lot of this stuff, right? So what that's telling us is that if I have something in the form of 1 over u, its antiderivative is going to be a natural log, all right? So this is a relatively simple natural log case because we haven't gone over u substitution yet, and so you might be thinking, well, I got to do u substitution. There's a u there. We don't need it for this particular problem, right? So it's going to be the natural log of t minus 20. This marker is killing me. It's like tailing off on everything. All right. We put the absolute value bars around it because t minus 20 could yield a negative result. And you can't take the log of a negative number. You can't take the log of 0 either, but symbolically we wouldn't worry about representing the time. So the natural log of t minus 20. So if you were to take the derivative of that, following the model, it would be 1 over t minus 20 times the derivative of the u, the derivative of the thing on the inside, which would just be a 1. All right? So we got what we need there. Again, for now, it's just more or less procedural. Down the line, it'll be, oh, now I understand why that works the way it does. So if you're ever wondering why the power rule failed for that one instance, you know, you were looking for the derivative, the antiderivative of x to the negative second. That was fine, but you did x to the negative first, and you got an error, and you're like, oh, it doesn't exist for that one. It does. It's just a natural log. All right. More on that later. So you're all very excited. Antiderivative of k with respect to t would be what? K, in this case, t. And we're going to put the plus c on the right-hand side for 2 reasons. One reason would be because we always put it on the right-hand side. The second reason would be because I really don't want to put it on the side with a natural log. It's going to be really messy. On the right-hand side, it's not pretty, but it's better than it could be. right? So now we have an equation, which is wonderful. The equation is not in its simplest form. We'll cross that bridge in a minute. But we've gotten rid of the TT. Now we only have capital T's and lowercase t's. We have those other constants we have to account for in a sec. But our first objective to get it out of differential equation form was met. So now we just have to do something. All right? Initial temperature is 70 degrees, so we can actually plug some stuff in and see where it goes. However, I recommend that you do a little background algebra first. Save yourself a little time and energy down the line. That being said, if you don't know log and exponential rules, then don't do this because you're going to get it wrong. Natural log is the same as log with a base e. That's not like the big aha moment. That's just something that everybody should know. You're like, oh, I do know log rules. Well, that's a good one to know, definitely. We want to convert into exponential form. Yeah, if you learn the Ben approach or the Logger-Dan approach or they're just the model, just knowing the different pieces of a log expression, that's fine. I like to use the circular motion because the base of a log is always the same as the base of the corresponding exponential. And if you work your way around, as long as you know what a structure of an exponential function is, then you would know that the next thing on the line, the next thing on the list of things to do would be to come up with the exponent and then the result of the expression. Okay, so this converts over to e to the kt plus c equals t minus 20. So it's a little nicer because now we don't have a log to deal with. And it also, if it's going to simplify down to a really nice, clean final answer, it's going to simplify through this process, right? It has to happen using this process. You can still get the correct answer working off of this because you have calculators, and calculators can handle what the question is requiring. But there are some good skills in here that can help us down the line. So, for example, I have a sum within an exponent. I can rewrite that as e to the kt times e to the c. All right. It's keep the base, add the exponents just in the reverse order. And we're splitting it up. You could always do that. If you had something like 2 to the second, you could think of it as 2 to the 1 plus 1. So that becomes 2 to the first times 2 to the first. You could always split up based on a plus or a minus sign. The plus sign converts over to multiplication. A subtraction sign would convert over to division. Right. So old algebra rules that don't always work their way into the problem solving, but when they do, they can be kind of startling when it happens. Quick question. E to the c is what? C. Okay. Don't lose sight of the fact that e is a number. It's a constant itself. So when I see e to the c, I see constant raised to a constant. Okay, so constant plus a constant minus a constant times a constant divided by a constant to a constant power, all give you a constant as a result. All right, the absorbing constant c. All right, so now I have, if I add the 20 to both sides, I have an explicit equation. Meaning an equation where I was able to solve for one variable in terms of the other. which is it's definitely a lot nicer than the natural log of the absolute value of t minus 20 equals kt plus c. Right? And also, if you're a calculator person, specifically thinking in terms of using a graph function on the calculator, this lends itself more to that, right? Because you can, it's y equals ready, so you can go right into the y equals menu and pop it in. You still need c and k, but it's going to be easier to work with it in this form. So we have an initial temperature. That means time t equals 0. Giving temperature, capital T, 70 degrees Fahrenheit. So let's pop that in. 70 for the capital T. C, E to the K times 0 plus 20. Anything raised to the 0th power is going to be equal to 1. Right? So we're looking at a simplified expression. On the right-hand side, it's just C plus 20. Oh, that's cool. This is what I want. Equals 70. And so that tells me that C is equal to 50. From here to here? Here to here? I divided, wait, second to third, so from here to here, I divided both sides by t minus 20, and then I just applied the integral. Oh, I also multiply both sides by dt. So it was this going that away, and this going that away. All right, so now we're looking at, I'll go purple here, t equals 50 e to the kt plus 20. So we're almost there. We need to come up with k now. Fortunately, we have a second condition that's going to allow us to do that. After 5 minutes, the liquid's temperature is 50, I can't even see, 50 degrees. All right, so that's telling us that t equal, lowercase t is equal to 5, capital T is equal to 50. So I'm going to pop in, let's go back to purple here. 50 equals 50 e to the k times 5 plus 20. All right. So we have to do a little bit of work here. So I'm going to subtract the 20 and then divide by 50. All right. So that's going to give me e to the 5k is equal to 3/5. All right, subtract the 20, you get 30 equals 50 times your exponential, and then divide by the 50, 30 50ths gives you 3/5. All right, so now it's getting a little bit better. I need to get k alone. Right? You have a variable trapped in an exponent. So fun problem, obviously, but now we get to convert back into log form. Again, if you're doing it purely algebraically. If you want to go to the calculator, you can try to solve it, but if I convert it into log form, that's going to release my exponent here. Right? So what I want to have is the log with a base of e. That's this guy. Of 3/5 is going to be equal to whatever the power is, 5k. That's why I like the circular motion way of converting from log to exponential form, because you know the base is always going to be in an obvious, I think, an obvious place. It's the lowest part, making it the base, right? So the base of an exponential, you've been using that terminology forever. The base of a log, it just looks like, if you look at the components that make up a log equation, And if you've never heard any of the vocabulary before, if somebody said, which one of these things do you think is the base, you're probably pointing to that. All right, so that's good. And then really, it's just a matter of knowing which piece goes where. So worst case scenario, you take a guess and check it with circular motion. E to the 5k equals 3/5. But it also turns out that if you place this as the base, if you have your exponential written in this form, so exponential component on the left, numerical component on the right, base goes in as the base, these two guys get swapped to go in your log. Yeah, so a lot of different ways of doing it that don't involve you memorizing some kind of acronym or something like that. All right, so what we have here is an ln of 3/5 equals 5k, which means that k is equal to 1/5 ln of 3/5. Okay, I'm just going to scooch this up a little bit. Tuck it in below. All right, so k is equal to 1/5 ln of 3/5. All right, so again, we were working off of this equation, this one right here. And all of that was just to figure out what k was. So let me do this. I'm going to write my new equation. We're going to say t is equal to 50 e to the k, all that stuff, 1/5 ln 3/5. There's a way to simplify this, but the way I'm going to show you makes it irrelevant. Times t plus 20. All right, so sorry about the handwriting. So this expression, I'm just replacing the k with this natural log component. And it actually simplifies very cleanly, but different story for a different day. Because I'm going to take, I think, 2 class sessions to really flesh out exponentials and logs, going back to the pre-calc stuff and then forward into more calculus-related topics. So if you're worried that you don't understand every aspect of logs and exponentials after this one problem, I wouldn't worry, because you're not supposed to. Okay? It's just to give you a little bit of a glimpse of what's to come. It's basically so that people look at this and say, oh, the class really, it is hard, I should drop. No. This is the worst case scenario, all right? So on a test, this will be the hard question. The worst case scenario would have you omitting this anyway, but you don't want to omit entire units of study from, like your curriculum. So, yeah, so just a little taste right now. Later on, we'll really flesh it out. So I'm not going to do that. So what we need to do, now that we have an equation, because all of that was just to get the equation, it doesn't even get us to the answer. How much longer will it take the liquid to decrease to 37 degrees Fahrenheit? So I need to set this equal to 37. So I'm going to put that in. I'm going to put a 37 degrees in there and solve. It's not an algebra course, although some calculus teachers think it is. Okay? I don't know how many. I looked at your information sheets, but I also looked at my other 150 students, so I remember bits and pieces of it. Yeah, I mean, there's always somebody who, this is their second go around with Calc 2. Or maybe they got a taste of it somewhere else, maybe in high school or something like that. If that's the case, you know what I'm talking about. You had somebody who insisted that you did everything by hand, no calculators. I have that a lot when I teach it over the summer. I'll have like 40 people in the class. 39 of them are from other schools, and the reason they're taking it here is because they know I allow the calculator. All right. So that being said, you have a calculator. Use it. Right? You can, if you want, take 37, plug it in, subtract the 20, divide by 50, convert from exponential back into log form, which I promise will be a very rich and rewarding experience if you like algebra. All right, I don't want to denigrate that. There is a time and place for it. It's just not here. All right, so let's get our calculators out and take a look at how we go about doing this without doing any algebra. Completely. Y equals. I'm going to put in 37 as y1. Then I'm going to put all the other fun stuff in as y2. So 50. So left-hand side goes in as one equation, right-hand side goes in as another. Second ln, if you're a real novice with the calculator, then you don't even know where to find an exponential button. It's second ln. Right next to the 4. Then we're going to put in the natural log component. I'm going to put it in a decimal form because they're clean decimals. 0.2 ln 0.6. That should all be self-contained, although it won't matter because of order of operations, as long as you get the parentheses around whatever's in the log. If you're in the exponent and you want to get out, for those of you, again, who are rookies with this, hit the right arrow. Plus 20. Yeah, you're going to put in an x because we don't have a t as an independent variable for this mode of the calculator. If you have a TI-83, when you hit the exponent key, a caret symbol comes up. When you do that, just make sure you put parentheses around every single thing you want in the exponent. All right. So we have our two equations. There's two ways to handle this now. One would be graphically, so actually looking at the graph. The other would be using the solver. All right, let me take you through the graphical approach. Maybe I'll say the solver for a different occasion because most people are going to do it using the graph. All right, so I could hit zoom 6, standard viewing window, but I don't think it's going to make much sense because I'm already starting with a fixed value of 20, which is not between -10 and 10. I have to go up to 37, which is not between -10 and 10. So definitely not the way to go. Window is a very important feature on the calculator. The patented explanation that teachers have used for years is play around with the window until you get a good one to see the graph, right? And that is probably the most frustrating thing because what that means is that you can't necessarily have a set process to come up with a good viewing window, and if you don't have a good viewing window, you can't get the job done. However, that was completely false. There is a set process that you can use to come up with a good viewing window, other than just playing around with the settings. All right? You have to understand a concept like domain, but if you do, then everything works out just fine. So let's go into the window. We can achieve that by utilizing the key marked window. You have x min, x max, y min, y max. Those are the ones that we're concerned with. All right, so let me snip this. And mark it up a little bit. I'll just pop it in here because we'll need it for the next problem too. All right, so we don't want -10 and 10. X min, X max is your domain. All right, so you want to think about where the function exists. Now, exponential function is infinite. And it starts at -infinity and ends at +infinity. It's everywhere continuous, unless there's some kind of undefined business going on in there, but not the case here because this natural log component is constant. So we're looking at something that's continuous and differentiable for all values of t. Long story short, that's just fancy language for that doesn't help us. All right, that didn't narrow things down. What I want to think about is a practical domain, a domain that makes sense within the context of the problem. Right? So t is what's going in as the independent variable. lowercase t is time, right? So we want to think about what values of time would make sense. Negative time, there's a time and place for negative time. We'll get to that in a couple minutes. But it doesn't make sense in this particular problem. All right, so we'll start off with a t value, a t min, or a y, x min in this case, of 0. An x max. All right, so let's just kind of make an educated guess here. It's saying in the problem, we had an initial temperature, so times t equals 0, good to go there. After 5 minutes, so I know I gotta go north of 5. How much longer will it take to get down to 37 degrees Fahrenheit? We're talking about something cooling from being in a freezer. I don't think we're talking hours. I think we're still in the realm of minutes. So let's try, you do have to make a little bit of an educated guess, but it's not a complete shot in the dark. Let's say 30. Let's say half an hour. All right, so it's an educated guess. I don't have room for educated. I barely have room for guess. All right. So the y stuff, I don't want to figure that out because that would be doing algebra. And if I was going to do algebra, I'd just solve the freaking equation myself. All right. So we want the calculator to do the heavy lifting here. So this is what you're going to do. And if you didn't know this before, it might prompt you to want to go back and start all your math courses over again. To be like, wait, if I knew that, I would have gotten an A in everything. All right, restart. You're going to hit clear, then zoom fit. So clear, then zoom 0. Zoom 0 is zoom fit. All right. People who don't pay attention during this process, they walk away saying, all right, zoom fit, got it. Put my equation in, hit zoom fit. No, that is absolutely wrong. It might get you some reasonable viewing window some of the time. This will get you the window you want every time. This is like a magical hidden feature in the calculator. I don't know why it's not hardwired in. It is life-changing. All right? You'll never have to solve an equation again if you know how to. All right? So let's put this stuff in our window. 0 as my x min. I typed the equation in, right? 0, 30. Leave y max alone. You can actually do the clear zoom 0 in either y min or y max. It's going to change them both. But I do it in y min. Actually, I don't commit to doing it either way, really. I do it alternatively, whenever the spirit moves me. So go to y min, hit clear, so it blanks it out, then zoom 0. Fully rusted metal, Batman. Movie reference, anybody? Obviously a Batman movie, but which one? Not the 60s, no. But that's the right kind of verbiage for that sort of movie, the Adam West. What's that? No, it's actually like a feature film with real people, like live action.
Yeah, that's what I was going to say, because the answer just keep us hanging over here.
I think I'll keep you hanging for a little bit. I want to give people the opportunity. You get that? All right, let me close. Approach, right? So in order to find an intersection between two equations using the calculator, the display has to actually contain the intersection, right? Otherwise, you're going to get an error message. So now we have a good viewing window. Let's find the intersection. So that's second trace, which is in the calculate menu. Option 5. If you have more than one intersection on your screen, you would scroll to that intersection and then hit enter 3 times. But we only have one intersection, so it's going to draw us right to it. So enter to select the first curve at the top of the screen. You can see what the first curve is. It's y equals 37. Enter to select the second curve. You can see at the top of the screen. That's what we want. So now the calculator knows to find the intersection between those two curves. The guess, I mean, this would be a bad guess, but I'm going to go with it. Hit enter. It's going to pull me right to that intersection. All right. So again, that's second trace 5. All right, so second trace 5, and then you hit enter 3 times. All right, so what that did was the equivalent, the calculator analog, I guess, to solving this equation for t when lowercase t with capital T is equal to 37. All right, so it just told us that because x represents time, lowercase t, it just told us that it's going to take a total of 10.5, 10.6 minutes to get down to that temperature. But it said how many more minutes. All right, so it's implying that the 5 minutes have already happened, and this is starting off at time t equals 0. So we subtract off the 5, so therefore about 5.6 more minutes. Because 5 minutes have already happened in the problem. That's not always going to be the case. Sometimes it'll say, how long does it take to get to that temperature? In this case, it said, how much longer would it take to get to the temperature? So there's subtle difference in word. All right. But it did all the algebra for us. So you just think about that for a second. Maybe you suck at solving trig equations. Maybe you just suck at solving equations. Maybe you just suck. I don't know. You just could just be just an awful human being. No, it's a time saver at minimum. Maybe it's a lifesaver. I can't promise that, but it definitely saves you a little bit of time if you commit to a little bit of muscle memory on this. Try it out. Don't let this be the only time you practice with this. So, for example, if I needed, let's do some trig. I'll do it real quick. Let's say I have, I don't know, something relatively simple. Sine of x equals, we'll go with 1/2. So I don't know any unit circle stuff. I'm in a jam. I need to know what angle gives me a sine equal to 1/2. All right. Depending on your mode, you'll get different types of answers. So I'm in radian mode. I can put it in degree mode if I want a cleaner number, but it's fine in radian mode. You could do a zoom trig for this because it's obviously trig, but if you know the domain, typically it's 0 to 2 pi. With trig problems, the domain has to be given to you in some capacity, otherwise you'd have infinitely many answers. If I go to y min or y max, hit clear zoom 0. Beautiful window. And I'll be able to get my solutions. All right. Now, we should know that a sine function only exists between -1 and 1. Right? That's the range of a sine function. But in a test, lots of things go out the window. This process, see, what does it give you? What does it give you? -1 to 1. It's not quite. It's a little bit rounded, but it's giving you a -1 to 1. So it's reminding you of the appropriate range depending on your domain. That's wonderful stuff. All right, so now I need an answer. So second trace 5. I'll just hit enter, enter, enter. It's going to drag me to one of the solutions, which is that guy. All right. So, and I know I'm kind of like, I don't want to say all over the place, but I'm really taking this down as calculator avenue because it will save you on several problems. Let's say you need an answer in radian form. there's two ways to handle it. One, put your calculator in degree mode, get the answer, and then convert that over to radians. The other would be to actually work off of this, right? So, nifty trick. Once you do the intersection function, you can quit out of here. Now every time I hit X, that X in your graphical display is the same X in your home screen. So it's stored your answer in as X. So you can work with this number now. So you don't have to worry about retyping it. If my answer is supposed to be in radian form and it's going to be clean, I know that this has to be some multiple of pi, right? Okay, so divide it by pi. It's that decimal. I don't know what that decimal is. Math bracket. Math, enter, enter. 5 over 6. All right, I divided by a pi. Let me correct for that by multiplying by pi. So 5 over 6 times 5. 5 pi over 6. All right, so unit circle without knowing the unit circle. That's your bailout when it comes to trig. I'll go over that process again when it becomes more relevant. Right now it didn't really apply, so you're kind of half in and half out, and I don't want to overwhelm you too much. But yeah, life-saving techniques.